All right, so this question is about a skier going down a slope. I love this question. It's pretty juicy, so I like to get into these kind of problem-solving exercises. The question is ultimately asking us, how long will it take? So just to recap, the skier is skiing down a slope. The slope is inclined at 25 degrees. They tell us the coefficient of friction between her skis and the snow, and they ask how long it will take her to travel a certain distance if she starts from rest. So they're looking for a time. So the first thing I'm going to actually do is organize my kinematic information. Delta x, delta t, v naught, va. I saw that, we're not just dealing with a's and forces, we're also dealing with distances and velocities and time. So we're going to make sure to, systematically organize this. So let's see. It tells us that they want to know how long, so that's my unknown. It'll take her to travel 45 meters down the slope if she starts from rest. So by now I hope you understand that you're getting get this information from looking at the forces. So this is my don't know, don't care. You have three other pieces of information, so you can solve for time. So now let's go over to the force side of this so that we can look at the information to see if we can figure out what A is in this example. So, sorry, I'm coughing during this video. So we're going to draw the forces acting on it first. So we've got the force of gravity, which is straight down. I'm going to stick with the red color motif of this problem. And then we've also got the normal force, which is perpendicular, straight up. Let me draw that a little bit over here. So there's my normal force, perpendicular to the surface. And then we've got frictional force, opposing the motion, force of friction. All right. Remember, we want to find the acceleration of the object. So we're going to, and when this person is going down the slope, they're accelerating down the slope. So my acceleration's in this direction. So I'm going to do what we talked about before with slopes, and that's rotate the axes. So I'm going to make my y-axis perpendicular to the plane. So you can just imagine it going like straight through there. And I'm going to make my x-axis right parallel to the plane like that. That wasn't super good. Let's see, like that. So that's my x, and this is my y. And now she's accelerating down the ramp. So we'll start off this problem looking at the x information. Or in this case, it's not horizontal, but it's sort of along the slope. Along the slope. And that's in the x direction, right? So what's happening in the x direction? Well, you've got the force of friction. Like, let's make our sign convention. We'll make down is positive and up is negative. Up the slope is negative. Perpendicular up is positive, perpendicular down is negative. Okay, so you can see that the force of friction acts backwards, so negative x along the negative x-axis. But also remember that this has to be taken into account. You can break the force of gravity into the x component and the y component. So I can draw it like this, and then the x component would be like this. Or you could draw it the other way, to be honest with you. Either way works, but you just got to look at the angle and make sure you know what you're dealing with. So if this angle over here is 25 degrees as labeled, then I think you can see that this is a right angled triangle. And therefore this angle, this one, let me make it a different color. Like this one will be 90 minus 25, which is what, 65 degrees? And then this one will also be 25. So you've got the x, y, and the x. So FG x and FG y, right? And then we can solve for those two things. Maybe I'll just do it over here. So in the x component, you can see that it's the opposite angle. So I can say FG x is equal to FG times the sine of 25. And remember, FG is just mg. This is just mg sine 25. Okay, we know all those things, so we can figure this out. And then for the y component of FG, FGY, it equals FG. And then you can see that the orange side is adjacent. So it's cosine 25. And again, we'll make that MG cosine 25. All right, so we put that in. Let's go back to this analysis of the x-axis. So we can see that the two forces acting along the plane or along the slope are the x component of gravity, which is the force that's responsible for accelerating her down the slope, and the force of friction. So we've got F net equals the sum of the forces, and this is in the x direction. That equals ma. All right, so the sum of the forces is FGX minus FF, which equals MA. All right, so let's look for those substitutions. We'll plug in FGX. Well, we already know it's MG sine of 25. And then FF is mu Fn, right? Fn, which equals MA. All right, so this is where what I said at the beginning when I said this is a juicy problem. It's like now we have everything, but we still don't have Fn. So we actually have to look at this problem along the perpendicular as well, if we're gonna, because we're kind of stuck right now. We have everything. We want to know A is my unknown. We know everything else, but we don't know Fn. But we can find Fn by looking at the y component. So let's just make a note of that. So we started here. So now look at y direction to find Fn, normal force. All right, so let's do that. And I'll do it right here. So perpendicular, what do we have going on? We have the normal force acting in the positive y direction and the y component of gravity acting in the negative y direction. So we can say here perpendicular to slope and this would be in the y direction. We have F net equals the sum of the forces. F net in the y equals sum of the forces in the y, which equals ma. What's the a in the y in the vertical, in the perpendicular direction? Hopefully you can see that the a is going to be 0 because it's not accelerating above or below the slope. It's only accelerating along the slope. So in the perpendicular direction, the a will be 0. So we have the sum of the forces, which is Fn pointing up minus Fgy pointing down, and that's going to equal 0. So therefore, Fn just equals, and then we can substitute what we have here, m times g times the cosine of 25. Now you could plug in the numbers at this point. I tend to leave them, so I'm going to leave them for this purpose of this problem. I think it's more elegant, but I get if you just want to turn that into a number, you can definitely do that. But now we see what we have now is we have Fn. So where that yellow highlighting is, I'm going to just substitute this expression in for that. All right, so let's do that right here. So now here, I'll say here, sub in Fn. Okay. So now I'm going to write the whole thing out. M times G times sine of 25 minus mu times, now it's M times G times cosine of 25. And all that equals M times A. So this is what I mean by it's more elegant to leave all the variables in. Maybe you can see this, but I've got an M in each of my terms. So I can actually cancel out the M. It's interesting because the mass of the skier actually has no bearing on the amount of friction or how quickly she'll accelerate down the slope. So the rate at which she accelerates is independent of mass, which you've seen before in free fall, right? We say it doesn't matter how big or small the object is. If we're ignoring air resistance and stuff, everything will fall at a rate of 9.8. Well, now the acceleration rate will be lower because she's on the slope, but it's still independent of mass. Everything increases as the mass increases, both the force of gravity pulling her down along the slope and the force of friction, and they both increase by the same amount, so it ends up canceling out. So this equation you can just solve for A. Is equal to, just like clarifying this a little, G sine 25 minus, and what was mu? Mu was 0.15, 0.15 times, I should put in the g here. So this is 9.8 times sine of 25 times 0.15 times 9.8 times cosine of 25. So that's a doozy, but then I think you'll see the acceleration is 5.6. I should do it just to make sure, because that answer is from a long time ago. So I'm just going to take a second here. Times minus 0.15 times 9.8 times. Oh, I get 2.8. 2.8 meters per second squared. Okay, so now remember what we wanted to do with this information. We wanted to plug it in over here. So let me do that. 2.8 meters per second squared. And then we're trying to find time, but we don't have, we want to find time, but we don't have the final velocity. So we're going to use the equation delta x equals VO delta t plus 1/2 a t squared. This will go to 0. We can plug in our 45, or let's rearrange the equation. We're solving for t. So t equals the square root of, let's rearrange this, delta x times 2 o over a. And then this is the square root of all of that. So t equals the square root of 2 times 45 divided by 2.8. So our t works out to 2 times 5.7. T equals 5.7 seconds. So my units were wrong that I wrote the answer in. So here's the time. And that's the answer. That's a lot of work. Okay, like just take a look at what we've accomplished here. So these problems are pretty, they've got a lot of heft to them. So what I would encourage you not to do is to despair. Just stick with it, follow the steps, ask me questions. Okay.